This is Gravity Practice 3, problem 61.7. We're actually going to split this problem up into two parts, a part A and a part B. This is the part A video, so if you're looking for part B, go check the next one. But what we're looking at in the next video are escape velocities. And we're going to see how fast we need to move in order to escape or to completely move out to an infinite distance away from whatever object that we're trying to escape from. If you have no idea what we're talking about, then you want to go back and check the CP Unit 12 escape velocity derivation. We take a look at how we get an escape velocity, what it means, and what we're looking at here. But if we're trying to escape our own solar system, then we need to escape the sun. That is actually the thing that we're escaping. Technically, we're escaping two things here. We're first escaping the Earth, but then all the velocity we have that we use to escape the Earth is then used to escape the sun eventually. So we kind of go from an Earth to a sun. And the way we're going to do this is if we think about, here's the sun, whoop, and we are all the way out here at 1 astronomical unit on the Earth. This is our position. We are trying to, set up some sort of launch that we use the Earth's velocity that it gives us, and then whing, we sling kind of out of it, and we get some escape velocity so that we never come back. We lose our orbit around our sun into outside of our solar system, and we're gone forever. So what is that needed escape velocity? Well, as we show in the other derivation video, we know that an escape velocity is equal to the square root of 2 times big G times the mass of whatever it is you're trying to escape divided by your original position from that object. Okay? This looks very similar to the orbital velocity equation, except there's a 2 that gets populated in here due to the fact that we didn't use centripetal forces to derive this equation. We used conservation of energy to do this. So if we take a look at what we have here, big G is a constant, but we are trying to escape the mass of the sun because that is, the object we're trying to leave out of our solar system. It's the most massive object here. It's gravitationally binding everything to our solar system. We're trying to escape the sun. Okay, we don't need to worry about the Earth because we are trying to get away from the sun here. We're just starting our position at the Earth. So this down here, this orbital radius, well, not orbital radius, but the starting position, that is the 1 AU because that is where we are starting. So if we want to find an answer here, and instead of writing the radical sign, I'm going to put a parenthesis to the 1/2. This is going to be 2 times G, 6.67 times 10 to the negative 11, that's G, times the mass of our sun, which is approximately 2 times 10 to the 30th, all over, and then our initial position where we're trying to escape from, which is 1 astronomical unit, and in meters, that's just the distance between the sun and the Earth, which is about 1.5 times 10 to the 11th meters. And all of this is to the 1/2 power, and that's where I get my square root. So at this point, this is our escape velocity. We should, when we plug it into our calculators, get an answer of 42,200 meters per second, give or take a little bit. So let's chug this all in and see what we get. Let's do 6.67 times 10 to the negative 11th times 2 times 2 times 10 to the 30th. This gives me 2.668 times 10 to the 20th. We'll then divide by 1.5 times 10 to the 11th. We get 177866667. Then we take this to the 1/2 power, and we get 42174, which is just about 42,200, give or take a little bit, but it's not a perfect circle for Earth's orbit, so this number might be slightly different. But that's a good velocity where if you have that, you're more than likely going to escape out of the sun. You're going to be able to get out to an infinite distance away from it where you'll just barely stop. But you can never really reach infinity, so that's kind of a weird argument in and of itself. Okay, but that's how we do a problem like this, using that escape velocity equation and where we're starting at. In part B here, we're going to change things up a little bit. We are not going to escape just from the sun. We're going to escape from a more massive object, whatever it is. And we're not going to start at the Earth's position. We're going to start somewhere else and see what happens. But for right now, this problem is finished. For part B, go check out the other video and take it easy. Adios.